know that's a lot to keep in your mind. Now let's look at the next thing. I have the partial derivative of f with respect to y times f times h squared here, right here. Partial derivative f with respect to y times f times h squared, because I have this multiplied together. Here I have the partial derivative of f with respect to y times f times h squared. What's in front of this one that I have right here? Well, there's a w2 times beta. What's in front of this one? It's going to be a 1/2 because I have this divided by 2 again on the outside. So I have w2 times beta is equal to 1/2. This is my system of equations. Now I can solve for w1, w2, alpha, and beta. I can solve for w1, w2, alpha, and beta. And again, if you're confused by that, just go back to the video and just kind of rewind it and look at it again and see if you can see where I'm getting this w1 plus w2 is equal to 1, w2 times alpha is equal to 1/2, w2 times beta is equal to 1/2. It's there, okay? Now there is, because of we have 3 variables, but we have 4 equations, this is not going to be a unique set of possible values you can get. You actually get a family of solutions for w1, w2, alpha, and beta. There's actually a family of solutions. There's not only one possible solution, but there is one of the most famous solutions, right? One possible solution is that w1 is equal to 1/2, w2 is equal to 1/2, alpha is equal to 1, and beta is equal to 1. Okay. So this is one possible solution. w1 is equal to 1/2, w2 is equal to 1/2, alpha is equal to 1, beta is equal to 1. Again, this is not the only solution to this system of equations. There's infinite solutions to this system of equations, but this is one of the more famous ones. So what happens when you plug into this one? What do you get when you do that? Let's come here. I'm going to erase this. Remember, we're doing this so we can solve for w1, w2, alpha, and beta here, right? So let's do that. Let's put in our w1 and w2, alpha and beta. So therefore, one approximation using these values is, here I have y of t plus h, which is my y sub n plus 1, is equal to y of t plus w1 is equal to 1/2 f of t comma y plus 1/2, okay, 1/2 f of t plus h, because alpha is equal to 1, y plus beta is also equal to 1, f of t comma y h, and then I have the h on the outside. I need another parenthesis. Okay, where we have y of t0 is equal to y0. Right, so notice that this is a weighted, right? Weighted derivative, right? Because I'm using a derivative at ty, and then I'm using the derivative at t plus h and y plus f of ty h, right? And we're going to essentially average those two guys together to get my new, better derivative. And this is called the second order Runge-Kutta method. or you can call it the Runge-Kutta method of order 2. Okay, the second order Runge-Kutta method, or the Runge-Kutta method of order 2. Now, if you've ever seen the Runge-Kutta method, and some of you guys might have seen the Runge-Kutta method, right? Of course, more than likely, this is the Runge-Kutta method of order 4. But if you have seen the Runge-Kutta method, you've probably seen it in a different form. And let me just write down the different form. Oh, before I do that, another name for the second order Runge-Kutta method, and I should mention this, is it called the modified Euler's method. Because I'm going to use that name in the homework, called the modified Euler's method. And essentially, that's what we did, right? We modified Euler's method, right? Instead of using just one, the derivative at one point, right? We use the derivative at 2 points, right? And we average those derivatives together to get a better approximation. And this is a better approximation than Euler's method. Now that we have this new approximation method, right, called Runge-Kutta method of order 2 or modified Euler's method, same thing. A lot of times what you'll see is you'll see it in a different form. Let me write it the way most people would write this formula. So we have the alternative notation. You'll see this. You see y sub n plus 1 is equal to y sub n plus 1/2. The 1/2 is on the outside. And in brackets I have k1 plus k2. Where k1 is equal to f of t sub n, y sub n times h. K2 is equal to f of t sub n plus h of n, plus h. Y sub n plus k1 times h. Okay. You have k1 is equal to f of t sub n, y sub n times h. Right? So essentially k1 is going to be h times this term right here. Okay, f of ty. K2 is going to be h times this term without the 1/2. The 1/2 we bring to the outside right here. So this would be f of t sub n plus h, t sub n plus h, comma, y sub n plus k1. K1 is really just this thing right here. So we just put the whole thing plus k1. So you use k1 in k2. All right. So that's a lot of times what people do, just kind of to make it kind of a little bit shorter in terms of writing it down, right? Because this is a little bit unwieldy when you look at it. So a lot of times this is kind of a shorthand notation that people will use. Let's look at an example, and we'll stop after this. And then we'll talk about Runge-Kutta method of order 4. We're not going to derive it. Don't worry. Don't worry. I don't think I have enough sanity to derive Runge-Kutta method of order 4, or enough time. It takes quite a bit of time to do that. So let's look at an example. I'm going to approximate y prime equals y minus t squared plus 1. Y0 is equal to 0.5. So it's our favorite problem. Using the Runge-Kutta method of order 2, I'm going to say using modified Euler's method. And let h equal 0.5. Let h equal 0.5. So if you look at this, let's just kind of write down our formula here. We have y sub n plus 1 is equal to y sub n plus 1/2 k1 plus k2. Okay. y0 is equal to 0.5, right? That's our 0.5 right there. Where k1 is equal to, and let's write that down, f of t sub n y sub n, t sub n y sub n. So that'd be, it would be y sub n minus t sub n squared plus 1 times h. And, or you can put h if you like. Let's just put h, just to be consistent. And k2 is equal to, in this case, what we have is plugging in. Well, I don't want to actually plug all that nastiness in, do I? Let's, instead of writing this, we'll just use that notation. We'll use this f of t sub n plus h, comma, y sub n plus k1 times h. Right. I don't want to just plug in all that stuff for t and y into my function. All right. So this is what we have. Let's do an example to kind of bring this home. Let's plug in some values here. Let's just do 2 of them, or 1 of them. So we have n, t sub n, y sub n. This is a good reason to use a calculator or Excel or Wolfram Alpha or something like this. I'm just going to do 1 point because 1 point is enough. So we have 0, 0, 0.5. And let's just do 1 iteration. 1, 0.5. Okay, that's where I want to go. And let's plug in some value. Let's find out what k1 is. K1 is equal to, when we plug it in, that's going to be f of 0, 0.5, right? This is my t, and this is my y. T0, and then my y0. And we could actually plug that in and see what we get when we do that. So we get 0.5 minus 0 squared plus 1 times 0.5. Okay. When you do that, I get 0.75. 0.75 for K1. 0.75 for K1. Okay. Now K2, I'm going to get some more space here. K2 is equal to F of T0 plus H, right, comma, Y0 plus K1. We found out that K1 was 0.75. 0.75. So let's plug those in. And then I'll put my new work up there. So I have F, T0 is 0, so this is, and H is 0.5, so this is F of 0.5, comma, Y0 is 0.5 plus 0.75, I get 1.25. So 0.5 plus 0.75, so this is F of 0.5, and then 1.25 is what I want to evaluate. So let's do that over here. So that's why I didn't want to plug that in up here, right? You can see why I just like, okay, that's K2, I'm just going to write in that form and not try to plug in because it gets complicated. So K2 we know is f of 0.5, comma 1.25. So that means my t value is 0.5. My y value is 1.25. So I'll get 1.25 minus 0.5 squared plus 1 times 0.5. If I did that correctly, I get 1. 1 is what I get here. So that's K2. K2 is equal to 1. And so y sub 1 is equal to y0 plus 1/2 of K1 plus K2. Okay. That's just for my first iteration. This is not y2 or y3 or y4. This is just my first iteration to get to y1. So y0 is going to be, what did we say y0 was? 0.5 plus 1/2. K1 is 0.75 plus K2, which is 1. And when you work that out, you get 1.375. Let's see what you get when you do that. 1.375. Now, the actual value of the solution at 0.5 is y of 0.5 is equal to, I have 1.425639. Of course, it goes on forever. Okay, it's my actual. So this is my approximation using modified Euler's method. Okay, here's my actual. Not too bad. Of course, I can get a better approximation by reducing h or using a more complicated Runge-Kutta method, and we'll do that later. Okay, but I wanted to show you this one. So now that I have y1, right, which is 1.375, right, based off of this, I can get y2 by doing the same thing, right? I will go through and iterate using y1's value to get to y2. Right? So I'm not gonna do it anymore because it takes a long time, as you can see. On the homework and on the test, I only have you guys do one iteration. So essentially going from y0 to y1 for a Runge-Kutta method, just because it takes so long to do it. Before we finish up for today with Runge-Kutta method of order 2, right? There's other Runge-Kutta methods of order 2. That's why I kind of said modified Euler's method, because modified Euler's method uses W1 and W2 being 1/2 and alpha and beta equal 1. But there's other Runge-Kutta methods of order 2 that are there as well. So suppose we use different values. Before we do that, before we do a different one, I do have a little bit of a side. If h is equal to 0.2 for the one that we just got you doing, okay, then the Runge-Kutta method of order 2, the modified Euler's method, it yields a value of 0.826, and the actual value of y of 0.2 is 0.8292986. So it's a pretty good approximation when you have a small value of h. Okay? Of course, it's the same thing that's true for Euler's method, but modified Euler's method is going to be much better approximation. But notice that you get all that complication because it's much. You get a lot of complication for that accuracy. All right. So now let's talk about, now that I've said that, sorry I had to get that out. So if h is equal to 0.2, we got a better approximation here. Smaller h, better approximation. Okay. All right. So suppose you had a different W1, W2, alpha, and beta, right? What types of methods would you get? So different values for W1, W2, alpha, and beta give rise to different rules or different methods. I'll say that. We have the midpoint method. And the midpoint method, we have that W1 is equal to 0, W2 is equal to 1, and alpha and beta are both equal to 1/2. Okay, this is the midpoint method. This is still a second order Runge Kutta method, just with W1 and W2 being different from the modified orders method. We have Hume's method. Hume's method. Here we have that W1 is equal to 1/4, W2 is equal to 3/4, alpha is equal to 2/3, and beta is equal to 2/3. All right, this is called Hume's method. This is another Runge Kutta method of order 2, right, using different values for W1, W2, alpha, and beta. But irregardless, okay, of the choice of weights, the local truncation error, the absolute error between the Y0 and Y1, and the approximation, is big O of H cubed.